And welcome everybody. Thank you so much for joining our live stream today. We have the usual suspects, Adam and Costa. Steve couldn't make it, But we also have a very special guest with us, Scott Neumann. He's one of the most respected educators in the GD&T world, and he has years of experience helping engineers, designers, and manufacturers understand not just the GD&T, but how to think behind the system. Scott is the president of GeoTol, one of the most respected GD&T schools out there, and he's also a vice chair on ASME Y14.5, Y14.5.1, and a number of other ASME committees. Today, he's going to be sharing tips for beginners, advice for experts, and taking your questions as well. Stay through the stream, and you could win a seat for a GeoTol Fundamentals course. Scott is giving away 3 of them. Scott, thanks so much for joining us, and it's great to have you here.
Yeah, great. Thanks, Joseph. Yeah, I'm here to teach a little bit of geometric tolancing for everyone. Usually I have much longer courses here, but Joseph invited me over here to touch on a couple topics and trying to do it something for the beginner, something for the intermediate, maybe something for the advanced user to try to get you to learn a little more knowledge about how geometric tolancing works, especially focusing on position tolerance is what my plan was. And then how do you calculate position tolerance? There's a couple of good fastener formulas, fixed fastener formula, floating fastener formula. So I plan to cover those. And then maybe some more advanced techniques like composite position if people want to sit through.
Absolutely.
For sure.
I've taken some of these courses with GeoTol before. I've got my book that I still use, and they're great classes. And learning composite tolerance has really changed my world. So I'm really excited to get into this.
Great. All right. What do you think, Joseph? Just kind of jump right in?
Yeah, I'm good with that. If you are, we can jump to your screen if you'd like.
Okay.
So for the uninitiated, what actually is GD&T for those who are in the absolute, most basic levels of any of this?
Yeah. Geometric tolerancing is for interchangeability on your parts. So if you have parts that are made by different suppliers or even different machinists and you want parts to interchange with each other. And, I have a neighbor of mine who's a history major, and, I said I specialize in interchangeable parts. He's like, interchangeable parts? Didn't we figure that out in the Industrial Revolution? Well, what we've been led to believe is that, we got full interchangeability, Industrial Revolution. We're all past that. But the truth is that, plus minus tolerancing is where that kind of started. That got us about 90% there. Plus minus tolerancing was a huge leap, to put tolerance on drawings and have quality control to measure everything. But plus minus tolerancing doesn't work for 3-dimensional variation. And as our parts have gotten a lot more complicated and more precise, the plus minus system just doesn't work very well. Plus minus is 1-dimensional. And I think plus minus works really well for temperature and pressure and voltage. It's too much, too little. That's all you could ever have. When you have a 3-dimensional part with holes that can vary, perpendicularities and position tolerances in different directions, plus minus tolerancing didn't really work very well. So geometric tolerancing is a new tolerancing language for interchangeability on 3D variations. It was invented in the 1950s by a lot of really smart engineers, and they passed along a document for us, Dimensioning and Tolerancing Standard by ASME. So ASME Y14.5. And I call it a big wiki document of just generations of engineers who've hey, this is what we figured out about tolerancing, add to it and pass it on. And then the next generation says, oh yeah, we added more to it. And then we pass it on to the next generation. So we keep learning about better ways to specify the worst case variation that would be possible. And the goal is to have a quality control system that accepts all the parts that will function and reject all the parts that won't function. So as engineers, we have to learn how to specify what is that line between, all right, these are all the good parts, these are all the bad parts. And geometric tolerancing just is this awesome language to communicate that.
Gotcha. Thank you.
Yeah. So that's what I thought we would kind of go into, is just a little more specialized way of how to handle that. I thought I would just start with kind of some basic stuff first. And, some people are like, oh, I already know position tolerance. Great. Let me just kind of get some beginners up to speed on how position tolerance works here. And then we can go into some of the calculations. I know users of Libre, the CAD system, you're probably more design people that are going to be creating drawings and coming up with the calculations. So thought I'd kind of do a baseline understanding and then show people how to do the calculations. All right. Well, what I have on the screen here is just a really simple plate. And I just didn't want to get into crazy datums or anything. Just keep easy datums and, back face is A. And hopefully this is functional. We want to pick functional datum features, but that's a topic for another time. But we got an easy B datum right here and then a C over here. So the goal is to create a Cartesian coordinate system, basically a coordinate system of how your part aligns in the assembly. And then with position tolerance, you specify where do you want the holes to be. I want the holes to be at 25 millimeters, 50 millimeters, 20, 35. So those define what we call the true position. True in our standard means perfect. So just the perfect position is set by your basic theoretically exact dimensions. So then the holes are given two tolerances. This is given the size tolerance. So you can't make it any smaller than 11.7. You can't make the size any bigger than 12.3. That's the specified size, not too small, not too big. And the other one, the important one I'm teaching here, is the position tolerance. Yep. So position says each hole has to be located, positioned, within a diameter of 0.6. And the 4x means that that's going to be multiplied or patterned out 4 times. In our standard, this is called a pattern. A pattern is like a repeat of something. Same thing that happens over and over again. So we have 4x size tolerance and a 4x position tolerance. And what I love about position tolerance is you can draw it. And so you just draw the cylinders 0.6, 0.6, 0.6, 0.6. And I love that symbol too. What's that symbol look like to you? Does that remind you of anything when you see that circle with the...
It's like crosshairs to me.
Yeah, it's bullseye, and
Call of Duty, FPS, video games.
Yeah, Call of Duty, that's it. Put your reticle on this spot, and then I'll give you a spot where you got a hit, and anywhere in this zone, we'll call it a hit.
Exactly.
Now, one thing you be careful with when I say a diameter of 0.6, how much can the axis actually shift off center, though?
That's a good one.
Half of that. Yeah, so just be careful we don't get the radius diameter mixed up here. When we do position tolerance, we always specify it on a diameter, so you can quietly mutter to yourself plus or minus 0.3, but out loud and on the drawing, we would always write it as a diameter of 0.6. So each hole's axis can shift within the diameter of 0.6. Another reminder is that this is a 3D tolerance zone, and PowerPoint makes me draw a lot of circles here. But I have to remind people these are really cylinders that extend the length of the feature. So by definition, position tolerance is a 3D cylindrical tolerance zone. A diameter 0.6 extends all the way through. And so if I were to take a cross section through here so we could see this a little better, this would represent our datum A. That's where the part mounts on that initial big plane. B I cut off, but that would be your B and then your C. So here's your C datum. And so the 25 will locate a theoretically exact location. That's what we call true position. True is theoretically exact position. Nobody could be exactly a true position. That's impossible. So we give them a tolerance zone.
Quick question that came up. How does reference A affect the holes in this example?
Yeah, that's a good question. You have to immobilize the part in 3D space. And so if I take my imperfect part right here, it's kind of like, what do you want to look normal to? Like, how do you want to align to the part? And so in this case, we're going to align to that A plane first, and that'll establish the initial 1 translation and then 2 rotations of the part. And then you're going to bump it down to our B plane, which will be our surface plate. And then we'll bump it to our C plane on the side over here. So it's like how you immobilize the part is what the datum reference frame is. So you're mounting it to that A, 3 degrees of freedom, B, 2 degrees of freedom, and then bump it to your C, 1 degree of freedom. Now you're going to locate these holes in 3D space. So pretty much every position tolerance, pretty much, there are some exceptions. They're going to have ABC there because you need a full coordinate system to lock it in space. And yeah, these datum features should be functional. How it usually mounts in the assembly. I've taken a very simple bracket, but as you get more complex parts, you have axis datums and center plane datums and more complex things, but easy plane for this one.
Thanks.
Which, if I can just jump in for my fellow Libre users, it's like what we do when we're assembling a part. It's the exact same mindset, right?
Yeah, when you first constrain the position.
Yeah, exactly.
your first part. So very nice.
Yeah, what a good analogy. Yeah, how you align it in the assembly, bump it to this face and then down to this edge, or,
Exactly. Yeah.
this shaft or this hole, or, however it ends up mating in the assembly.
Yep.
Yeah, great comment. Yeah, so big thing I remind you here is position controls location. That's its primary use, is to locate that hole within its plus or minus 0.3. But because of the 3D nature that you get here, you're also going to get a free orientation with it. So you also control perpendicularity, parallelism to the datum reference frame as well. Yeah, very powerful tool.
Good stuff.
Yeah, that's kind of the basics of position tolerance. That's what I wanted to start with there. And so now people understand what position tolerance is and how it works. Then I was thinking about showing you how to calculate the value. That's kind of the big question people get. They're like, okay, I understand position tolerance, but how do I calculate the number? Like, what number should I put on my drawing? And especially for clearance holes for bolts and fasteners, we have some great formulas for us that are in the standard. Now, this is in the appendix, non-mandatory appendix B of the standard, and just kind of taking the information from there that's been passed down since the 1950s and putting into a lesson for us to learn here. I actually have this lesson in both of my books. I have it in my fundamentals book in Unit 12, and I also have it in my advanced applications and tolerance stacks book in Unit 7. Because it is really a tolerance stack, a tolerance stack of a lot of different things. What is a tolerance stack? It's a multiple tolerances that you apply that stack to create an even worse overall condition that we have to account for. So here we have a couple of parts, a orange plate and a blue plate, and they have clearance holes in both of the parts. And then when you drop the bolt through and you put a nut on the other side, they say that fastener initially floats in there. So that would be a floating fastener situation. Fixed fastener is when you have threaded holes in one of the parts and then clearance hole in the other. So then the bolt would clear through the clearance hole and then self-center into one of the parts. That's what they call it, a fixed fastener. So that's the question, is the fastener self-centering into one of the parts, or is it just clearing through a couple of clearance holes? So what would a rivet be? Would a rivet be floating or fixed?
Be a floating fastener.
Yeah, rivet would be floating, because in a riveted assembly, you might have a couple holes that look like this. And as long as you can get that rivet to slip through like that, you're good. So you're not self-centering in either one of them when you initially put it in. But what about a pressed dowel pin?
Well, I'd say fixed because it's pressed in one of the holes.
Yeah, if it's a press fit, yeah.
Self-centering into one of the parts and then clearance in the other. So that would be an example of a fixed fastener. How about a welded stud and a nut?
Fixed. If it's
fixed,
welding that stud, yeah, you're definitely fixing onto the part. So that would also
welding it
for like machined in pins, like a lathe pilot or something, or plastic parts with formed pins. Those would be fixed. I would say most parts are going to go together with fixed fasteners, but I don't know. There's still floating ones out there too. So I would say we should learn both of them. Makes sense.
For sure.
Yeah,
absolutely.
Nuts and rivets are probably your most your floating fasteners. Everything else is pretty much fixed.
And we have a comment or a question here. What is the box around the dimension? I think he's probably referring to basic dimensions.
Yeah, let's go back to that. So box around the dimension, in ASME, we call it a basic dimension. And I actually don't like that term. I don't think it hits hard enough. It's a basic dimension. It sounds like it's just a simple dimension or something. ISO, I think, really nails it. They call it a theoretically exact dimension.
I like that term. That's really
cool. Man, they call it the TED, right? The theoretically exact dimension. It's like the theoretically exact dimension, like where it's supposed to be. And the purpose of those is to tell you where perfect location is. Like, what's perfect? What do I aim for? It's basically where the dartboard is on the wall. It's at 25 millimeters and 20 millimeters from the floor and the sidewall. So aim for that. Now, nobody can be perfect. So that's why we assign our position tolerance. And we assign that in a diameter value because that's what the shape of the dartboard is, and the size of our bullseye. We want it to be that shape of diameter. So yeah, it's a basic dimension, theoretical exact dimension, no tolerance, basically no tolerance on the basic dimension.
Gotcha.
And
Very
can I
good.
just
Good.
can I just point out that theoretically exact is how I got taught that, right? Which is because I'm in Greece, so we're following the ISO standards, but they are harmonized, right? And this is the beauty of it, right? This is a language you can converse with people from basically almost the entire
All over the
planet,
world.
right? Yeah, exactly.
Yeah, that's the thing with ASME and ISO. We have similar concepts. It's just sometimes we name them a little different. Like, oh, we call something an elevator, and they call it a lift, and we call it a bathroom, and they're like, what are you talking about? It's a toilet, or a water closet. It's like different names for this concept. And I kind of do like ISO standards terms sometimes. I'm like, oh man, that's a better way to say that. But we kind of have a lot of legacy stuff where, all right, we don't want to change too much. We've always called it basic. Do we change it now, or do we just live with basic? So yeah, I do really like a theoretically exact dimension. I think that really hits hard and tells people, yeah, no tolerance on that. All right, well, great. Let's learn both of these formulas for the calculations on our position tolerances here. So we'll start with the floating fastener. So that's where we have our two parts, the orange and the blue, and the orange has clearance holes in it and the blue has clearance holes in it. And the ultimate goal is to make sure that the orange holes can't be off their perfect location too much, and the blue holes can't be off their perfect location too much before it won't assemble anymore. So how do we assign the tolerance for this? Well, easy datums on this one again. So just those edge datums. Again, hopefully they're functional. And that's for another video of picking functional datum features there. We have basic dimensions. I'm going to do inches this time. So 1.5 inches, 625, 625, 1.2 inches. And then the same thing on the other part. They pretty much match. You got A, B, C. And all the dimensions are lined up perfectly in the Libre CAD system there. Then you usually start with bolt size. What size bolt do you want to use? So in inches, they decide to go with a 1/4 bolt. That would be a 250 mmc. Bolt tolerance will always go minus. That is nice. So when you have a 1/4 bolt, you have an M8 or an M12, that's going to be your MMC, your maximum material condition, biggest pin. And then bolt tolerance will go minus. So then we use that to come up with what size hole you want to use. You don't just pick some weird size hole. You usually pick a standard drill that we have out there in the shop. Inches, I know it's a terrible system. That's what we use in the US. So we use inches, and the drill sizes go up by 64ths of an inch. Ooh, yeah, it's bad. So 1/64th would be a normal clearance hole, and 2/64ths, or 32nd of an inch, would be an oversized clearance hole. And that's what we're seeing here. 281 is 1/32nd bigger than 250. It's 9/32. Okay, so then you look at drill charts, and they'll recommend a little more plus than minus usually on drilled holes. It's because when a drill becomes dull, it tends to walk and wobble in a hole. So giving the life more life on the tool by giving it more plus than minus. That's what we have, standard drill size and recommended standard drill tolerance there. Okay, so how do we make sure that these holes aren't off their mark too much before it won't assemble with the other part? We use this formula. The formula is smallest hole, biggest pin. So hole MMC stands for maximum material condition. That's another name for smallest hole. So worst case hole, smallest hole, minus your biggest pin. Maximum material condition of the pin. Smallest hole, biggest pin, how much room you got? So how much room you got between your smallest hole and your biggest pin, and they came up with a clearance of diameter 29. And with position tolerance, with floating fastener, you can give that as position tolerance each part. So I gave a position of 29 to this one, and I gave a position of 29 to this one. And that's the formula to ensure interchangeability. Now, how do you know that'll work? Well, you can just trust me. No, I'm kidding you. I got to prove it, right? So let's prove it out. So proving it out, you have our hole, and we're going to do worst case hole. So that would be diameter 279. And that's perfectly located in your Libre CAD system there. So then you're going to mate the blue part to that. And when you aligned it in CAD, it's going to look perfectly aligned, and I'll draw it right on top of it. That's the blue hole, perfectly aligned like that. Good. Now we're going to insert a bolt, and that bolt is going to be significantly smaller. Remember, that was designed at a size of diameter 250. So then how much can these holes be off before they hit? So this says a position within a diameter of 29. So how much can the orange axis shift off center?
14 and a half.
Oh, he's
0.
good at 2. Yes, half. That's right, half. And that's the key there. When you say position diameter 29, you're saying the axis can shift half of that. He's right, 14 and a half. And so worst case, if the orange hole shifted 14 and a half this way, and then the blue hole has a position tolerance, and it has to be within the same diameter 29, but it can move half the other way. So worst case, you're going to have an assembly that will look like this. Looks like a Venn diagram. And the Venn diagram has just enough overlap for the 250 fastener to slip through both.
Exactly.
And so that little Venn diagram thing is playing at each hole location. This hole can be, here, 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 here. And then this one could be here, 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 here. And this one is here, 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 here. But then you have that just enough white overlap between the orange and the blue. And that's that what we call a virtual condition. And that virtual condition is enough for that 250 fastener to slip through.
Here, here.
Nice.
This is the good stuff, guys.
Yeah, this is really good stuff.
It's an easy formula, isn't it? Once you understand it, it's like, wow, this is really easy. Why is it so easy? Because they made it easy.
Yeah.
They're like, oh, you got a diameter hole and you got a diameter bolt, use a diameter tolerance zone. That makes sense, right? It's just worst case. Smallest hole, biggest bang.
Definitely.
Makes me that much more upset when my furniture from Walmart doesn't fit together. It's not that hard. I don't know how we got it wrong.
If I remember my numbers right, this gives you 56% more tolerance than if you were using plus minus dimensions, right?
That's right. Yeah, plus minus. Oh boy, that's a nightmare system. Because you have to put plus minus on instead of position tolerance. That's what we used to do in the 1800s and early 1900s. We used to put plus minus on the dimension, and
on every single one.
Yeah, and you put a plus minus here, and you put a plus minus here, and then you put plus minus on this. And it's a stack up nightmare. It really is. Like, I mean, this dimension has tolerance and that dimension has tolerance and this dimension, double tolerance because it stacks on itself. And it's like, and then you got perpendicularity, which you don't account for either. And you're like, oh gosh. So how do you do it? It's just,
it's just like 3 or 4 or 5 Pythagorean theorems, right? You solve it, reverse solve the Pythagorean and that's it. No big deal, right?
That's right. Yeah. You just, And you end up just over tightening the tolerance so much to make it like almost unmanufacturable.
That's actually very true.
Yeah, so it's really a far better system to allow maximum tolerance possible, but make sure it functions every time. Isn't that the 2 ultimate goals of a design engineer? I mean, number 1, make sure it works every time, right? That's pure function. And number 2 is maximize manufacturing tolerance. Yeah, and like Joseph said, gives you 56% more. I mean, I'd even say more than that when you start thinking about all the stack up that can occur. So yeah, use position tolerance way, way better.
I wasn't even thinking about stack ups at that point. That's a good point. You do get more after stack ups.
Yeah. If you just locate one hole, then this one hole square versus round, and it's like, oh, okay, great, you get 56% more. But then when you go to the next hole where there's a stack up, oh my gosh, you get even more.
Then you eliminate a whole bunch more human error as well, because it's just so much easier to read that one box versus, a plus and minus on every single other dimension trying to figure out what you're supposed to be doing.
That's it. Manufacturing loves it too. They can just look and be like, oh, there's my size tolerance. That's how big and small it can be. And then how much can I be off? And there's just one number in the box that tells you can be off a diameter 29, plus minus 14 and a half in either direction.
Yeah.
And there's human error in QC as well, in quality control, right? We always need to remember about that as well. So if you have less work for QC as well, that's another layer, right?
Yeah, it really cuts down on the number of things you have to inspect, because before it was like, all right, I got to inspect the dimension, this dimension, that dimension, this dimension. And now we're saying don't inspect all the individual dimensions and angles, instead inspect this position tolerance. And it becomes a lot easier to bubble up a print. You got your inspection bubble number 1, inspection number 2, and that's all you have to look at. Did you meet the size tolerance? Did you meet the position tolerance? Well, let's do just a quick practice problem on it to make sure people are good with that. Let's say we had a little design change come through on this. You know how engineers never make mistakes, they make engineering changes. So we have a little engineering change came through on this, and they had to add a shim to this. So the shim is going to get sandwiched between the parts right in between here. And assuming the same datums and the same basic dimensions and everything, the holes in the shim are 295 plus or minus 5. So we need to calculate what is the position tolerance these holes need to have to make sure it clears and fits through this assembly. Now, assuming they have the same size bolt and everything, so same size bolt is a 250 mmc, what would be the allowable position tolerance for this set of holes? And I did give you a multiple choice if you want to pull in on that.
I'm going to say A, 0.04. I want to know what the chat thinks, so I could be completely wrong.
Yeah, the chat's about 10 seconds behind, but we'll see it come up here.
No, we're just that fast and not 10 seconds behind. I would go for A as well.
Okay, well now I know that I'm more confident in Costa's answer than my own.
Well, 2 answers gives you a consensus?
Well, he knows what he's doing, manufacturing professional, 3D printing hobbyist,
Man, I'm good enough to know that I don't know what I'm doing all the time.
Yeah, you are correct. It is A. It is 40 thou. That's right. And how do you calculate 40 thou? Smallest hole, biggest pin.
Yep.
So what's your smallest hole? 290. So we call MMC. And then what's your biggest pin? 250. That's also what we call MMC. Smallest hole, biggest pin. How much room you got? How much room you got between your smallest hole and your biggest pin? And that's 40 thou. Yeah. And it's easy because it's all diameters, right? Holes a diameter, bolts a diameter, and then your tolerance just inserts directly in as a diameter. And one trick I tell design people is you don't care about nominal. If you're a design engineer, you don't care about nominal. You care about worst case, smallest hole.
Exactly.
Smallest hole.
That's so true.
Smallest hole. Biggest pin, but smallest hole. Yeah. So yeah, machinists usually care about nominal. That's like what they aim for. I'd recommend to aim for the middle, 295. But yeah, if you're a design engineer, you got to look at your worst case. Now,
sorry, but having worked on both sides, machinist and designer, machinists care about the tolerance as well because that's where the cost is, right?
True. Yeah, they're definitely looking at that range, right? They're looking at the distance between your goalposts, and they're like, all right, I need to kick a field goal out here. How big is this field goal? What is the width on my zone?
Good analogy.
Yeah.
Here's
that range between the goalpost, from a 290 to a 300. That's what they got to put that size of a hole in there. And then they also have another spec, make sure you're accurate. And this is pretty loose tolerance here, 40 thou, but maybe for a shim or something that might be necessary.
We've had a question come in: how to decide the maximum hole diameter to have an assembly as compact as possible? Kind of an interesting design question.
Yeah, it is. You don't want to make the hole too big, especially on like a bolted hole assembly or something, because if the orange hole goes too big, like 287 or something, then the head of the bolt will go through the hole, and then you got to use like a big washer or something. So there is a limit on how big I can go before you don't get the clamping pressure on there. So that's like kind of another design aspect you got to do, is like smallest hole, biggest pin, but how big can I go on it before it doesn't work the way I want it to? And also you could have a problem with this pink shim, the hole gets too big and then the shim starts shifting in there and rattling around in there and sticking out the side of the plates, and that would be bad too. So that's kind of like another aspect of it, more of a stack up issue of just, I don't know, what can you handle? And that's going to be LMC minus LMC. So it'd be the biggest hole minus your smallest pin. That'll be a stack up rattling issue. But for general clearance holes, like a bolt and a screw, usually the biggest hole doesn't matter too much. They're just clearance holes. Just don't let the head of the bolt go through the hole. So there's some, standard drill sizes and, standard clearance holes that people recommend for bolts and stuff like that.
Perfect.
Nice. And a good question there from the chat.
Yeah, it was. MMC modifier, I don't know if I have enough time to talk about that, but that gives you a bonus tolerance. It gives you a little extra tolerance. And boy, that might be for another time there. But what it says is that when the hole is at its MMC, the smallest hole, then you get the 40 thousandths. But as the hole gets bigger, then you can get this additional, what we call bonus tolerance, additional bonus tolerance. And that's appropriate for this situation because all the calculations were done at worst case. So as the hole opens up, you can have this additional bonus tolerance provided by the MMC modifier. All right. Well, I think we're pretty good on the floating fastener. So with that, I thought we'd pivot to the next one, fixed fastener. Sound good?
Yeah.
Let's go for it.
Sure.
All right. So this one is just slightly more complicated, the fixed fastener. So this one we have threaded holes in the bottom, and then we have clearance holes on the top. And I tried to keep it in inches again, just so you kind of see they're very similar, just one little modification to it. So you have to put your thread spec on here. So this is inches, and I don't know if everybody uses inches here. Probably a lot of metric users in the chat here too. But this is a 3/8, 375. That's the major diameter of your screw. In inches, you put the number of threads per inch. So in an inch of threads, there's 16 of them. UNC, Unified National Course Threading, and then the class of fit. And then B is for internal, A is for external. Now, the only number that really matters is that first one for our position.
May have had a brief freeze here.
Yeah, seems like it.
Yeah, I think he's just refreshing and coming back in with us for a moment. I really like this insight from the chat here. Bonus tolerance from MMC helps a ton, and it's so realistic. When your hole gets bigger, you really do get more ability to fit things together.
Oh man, it actually makes a difference on the bottom line. Let me tell you, right? And the larger your production run, the larger the difference. So
yeah. Well, we're glad you're with us, LGR FBS. Don't worry about being late.
And since we're discussing the inch V metric and we're discussing fasteners, do you want an interesting tidbit on that? So metric specification is, but we're getting Scott back. Metric specification is nominal diameter times pitch, whereas the inch one is the diameter and threads per inch. So the metric one is easier for the machinist to know what he's doing, right? You take the nominal, you subtract the pitch, and you get your pre-drill diameter. Whereas the TPI one is easier for the engineer to calculate if the fastener can take the load, the preload you want to apply. Because for the preload, you need to calculate how many threads are in engagement, right? And the effective diameter of your bolt. So inch is easier to calculate loads. Metric is easier to manufacture. There's an interesting tidbit for you.
Interesting. Yeah, that makes a lot of sense. Oh, and we got OmniCubed with us.
Hey, OmniCubed.
Well, we're just working on getting Scott back here. How about you all tell us your favorite jokes in the chat? OmniCubed had a great one last time.
I had a horrible one last night.
Oh, and we've got Scott back, folks. Let's jump in here. Welcome back. Sorry about that little burp there.
Yeah, I don't know what happened.
Internet happened.
Yes.
Yes.
Yes, this is how it goes when we are live, so not to worry.
Okay. All right. Well, great. Well, I think we're back here. Well, I think we were just introducing the fixed fastener formula, so maybe I'll just start again on this one. Yeah,
absolutely.
Fixed fastener, you have threaded holes on the bottom. So here's your thread specs, 375-16 UNC 2B. And the first number is really all that matters. That's your major diameter of your screw. So then when you go to your clearance holes in the other part, you don't just pick, again, some weird size hole. You pick a standard drill that we have out there in the shop. So that'd be a 32nd over is what they did on this one. So 406 is a 32nd bigger than that. Then a little more plus than minus to account for that drill wobble again. All right, so now how do we calculate the position tolerance? Well, the formula starts the same, smallest hole, biggest pin. So smallest hole is a 404. Your biggest bolt is that 375. So you get that same clearance again of 29 thousandths. Here's the only difference. You divide that between the parts. So in a floating fastener, you would give 29, 29. But in a fixed fastener, you have to split that 29 between the parts. So you give some to the clearance holes, and you give some to the threaded holes.
Joseph, don't forget to swap the scene back. There we go.
Okay, sorry.
Yeah, so that's it. Smallest hole, biggest pin again. But instead of giving 29 with a floating, we have to split that 29, give some to the clearance holes, some to the tapped holes. And you could split it any way you like. You could give one of them 14.5, the other 14.5. You could do 10 on one, 19 on the other. If I was making one of the parts and Costas was making the other, I would give myself 28 and he would get 1. But he's much better at manufacturing than I am, so that's why I need it. But yeah, you can split it any way you like on these. A general rule for splitting is a 40-60, and that's kind of a rule of thumb that floats out there in industry is a 40-60 split. So we give 40% to the clearance holes, and then we give 60% to the tapped holes. By the way, I call them tapped holes. The standard calls them tapped holes, but same thing as a threaded hole, tapped hole, threaded hole, same thing.
Yeah.
Okay, so why the unequal split? Why do we give a little less to the clearance holes and a little more to the threaded holes?
That's a very good question, actually. Why is that? I would imagine that I might show. I often say that I've worked as a machinist, but I don't accept the title of machinist. I'm not that good yet. But I would think that top holes are easier to get straight. Well, no, they're not, because is it because you stuck up the tolerances from the pre-drilling and the threading operation?
That could be a reason. Yeah, people say, well, there's more things to go wrong, right? You got to drill it, then you got to tap it, more things to happen. But actually, it's one that I haven't talked about very much. It's because of the MMC modifier. And the MMC modifier gives you this extra bonus tolerance. All the calculations are based on the 404 hole, and that's where you get the 12 thousandths. But the MMC modifier says if you make the hole bigger, you create more room, you create more clearance. And so we could use that as additional position tolerance. So it's the 40% plus the bonus tolerance you get from the MMC modifier is going to be about equal to 60% when you keep it regardless of the feature size. So that's the reason why, and it's hard to come up with that because we didn't really go over the MMC modifier very much, but basically what it says is at a 404 size, that's your MMC size, you get your position tolerance of 12 thou. Now, if the hole gets bigger, it goes up to like 406, 407, 408. So let's say it goes up to 409 size, you get this bonus tolerance up to 17. And if it goes all the way up to LMC, you have as much as 413, you would have as much as 21. So you get this additional position tolerance. And the idea is when you hit about the middle of the size range, when people hit 406 and it wobbles a little bit, they'll probably make in the middle 409, then it equals out with the other one. So it's because of that bonus tolerance that we didn't get a chance to explain real well, but as the hole gets bigger, you get more position. You don't get that benefit with tapped holes.
Makes sense.
We had a question that came in. How can we calculate tolerance value for dowel pins? Fixed fasteners case seems not the right way. Is there any better approach? Or
nope, that's it. Dowel pins is fixed fastener, smallest hole, biggest pin.
Yep.
Yeah, so same idea, like how much room you got between your bolt and the hole. And the amount of clearance that you've designed in is the geometric error that can occur. And that's either going to be position or perpendicularity, and really the combination of both when you do position, that the clearance you have between worst cases is what you can give away as that extra position perpendicularity.
Fantastic.
Well, great. Yeah, that's the fixed fastener formula. I guess we should maybe talk a little bit about the projected tolerance zone. I think that would be a good one to discuss. Yeah, that's a really cool modifier. Boy, that is a underused and underappreciated modifier. It's really cool. So let's look at position tolerance on some threads here. So I kind of zoomed in on this view of it, and we have a blind threaded hole here, and it's located by the basic dimensions. And then I have kind of a cross section of what the green part, the clearance holes, would be on top.
Yep.
Now, let's say you do a position tolerance, no projected tolerance zone modifier. what is the shape of the tolerance zone and where is it on the
circle?
And make sure you do a 3D. So cylinder.
Cylinder, yeah.
Yep, cylinder. And that cylinder is going to be located at the true position, the theoretically exact position, and it extends the length of the feature. So for the purpose of position tolerance, remember, is to control the location of the axis. How much that axis can shift back and forth, that would be limited by that cylindrical tolerance zone that you have. But remember, position also controls perpendicularity. So it also controls how much it can tilt in there. Now, that axis is within the tolerance zone, so we would call that a good threaded hole. It's within the position tolerance. But look what happens when you put a bolt in there. The bolt is going to want to take off in that direction, and it's going to cause what we call projection error. Because the axis of the bolt sticking out will be way further off than what you originally spec'd out with your cylindrical tolerance zone of 17. So yeah, that's what we call the projection error. And you can calculate this projection error. This is the depth D, that's the depth of engagement, the depth of your threads basically. And then P is the projected height of your fastener, which will basically be the clearance hole's thickness right here. Now, just eyeball this. I did this in PowerPoint, so not the best here. But if this was shifted 17 down here, just kind of guess, eyeball it up here. How much do you think it could be worse up at this projected height? 2 times worse? 3 times bigger than the original tolerance? 5 times? What's it look like to you?
Looks like twice, twice more, right? Isn't it like?
It's actually 3 times more.
3 times, huh?
Yeah, that's 3 times more. So they give us the formula in the standard. The tolerance at the projected height is equal to T0, which is the original tolerance that you spec, times 1 plus 2P over D. So if you do P equals D, which I think is pretty common here, where your thickness of the green part, the thickness of your clearance hole is about the same as the thickness or depth of your threads, then you do 1 plus 2P over D, P equals D, so 1 plus 2, it's a 3 times multiplier. It's crazy that the tolerance you spec down here could be 3 times worse just by sticking out one extra plate thickness out. And it gets even worse if this was a projected height of 2 times the depth of the threads, then it becomes a 5 times multiplier. Now, obviously, it's going to be a lot smaller if your mating part is thin. So let's say your projected height is only like a quarter, like a sheet metal or something like that. But honestly, it's still pretty significant. I mean, it's a 1.5 multiplier on your tolerance. Okay, so how do we solve this projection problem? Well, there's 2 solutions to the projection problem. One of them is to tighten up the tolerance. So you just tighten up the tolerance. So if you reduce the amount of position tolerance down here, and you'd have to reduce it down to 1/3 of your original, because remember the projected height tolerance is going to be 3 times the original. So you'd have to cut your position down to 5.5 to get your functional 17 cylindrical zone. But there's a better method, and that's to project the tolerance zone. So that's what this P modifier does. We call it a modifier because it modifies the tolerance zone, and I don't want it to extend the length of the feature anymore. I want it to be projected out of our threaded hole, and then you always specify a height, the 502, which is the thickness of the mating part. So watch the tolerance zone now. I'm going to modify it because now it's going to shift up, and now it's no longer existing down inside the threaded hole. It's now going to be shifted to be up here. So now the axis of our threaded hole has to be good here and here, and nobody cares about the position at the bottom of the tapped hole because that doesn't mate into a clearance hole. So that controls the tilt of that at that projected height, but the great benefit is it still gives you all that great position tolerance. You still get a position tolerance of 17, where this one tightens up the tolerance down to 5.5. Well, why are you tightening my tolerance? Well, you might be tilted. Well, how about you don't judge me on what might happen? How about you judge me on what did happen?
Yeah,
and that's
exactly
actually what the clever thing with the projected tolerance zone is. Judge the real part and look, will it be in the right spot? Will the bolt be in the right spot? That's what we really care about.
It's like, let me just say that this, you can actually see, guys, why this is so many decades of condensed like manufacturing experience, right? You can really see it. It's not just like dry numbers in there. Once you hear why this is like that, it actually makes a lot more sense. And can I also just note that tilted bolt that doesn't go through the clearance hole, that gave me PTSD, but that's fine. But please go on with
Yeah. The thing is too, I say that, it's just going to cause interference, and really what happens, you put the torque wrench to that thing, it's going in, right? So you're going to end up cross-threading stuff is what really happens.
Cross-threading is shifting the top plate, and then another part doesn't fit, and then another part doesn't fit, and then you're chasing. You think that the problem is with the other part that doesn't fit, where this is where you made the error. It's so much simpler to just think of it and specify it properly.
Inspection loves it too, because let's say you have a part that has some, blind tapped holes in it like this one. So let's just say these are blind tapped holes going into the part. So how do we check it at the height of the part and then sticking out? Oh, just use a thread gauge. So stick a thread gauge in there. I think I got a couple thread gauges. Yeah, there we go. There's a thread gauge. I got a few of them here. There's another thread gauge. Another thread gauge right here. So now when I stick these thread gauges in there, I'm checking at the base. That matters, the right position tolerance. But then also you're coming out that height that you specify the remaining thickness, and then checking to see, is it good here also? So you're really making sure you check here and here. And that's a benefit to inspection, because if you don't have the projected tolerance zone, you're supposed to check it here and down into the tapped hole down here. And it's like this blind hole. How are you going to find the bottom of the tapped hole? Oh, don't find the bottom of the tapped hole. We don't care about that. Find the bolt that's sticking out and measure that. So it gives you easy access to measure here and here where it actually matters.
That is the nerdiest pencil holder I've ever seen.
Got lots of thread gauges in here. Yeah.
Yeah. So cool.
Yeah, and Costas said it too. He said, "Boy, this is just legacy of just so many awesome things that have been learned over the years." And I saw this projected tolerance zone. I'm like, this is so clever. Like, where did this come from? And so I was digging back into some of my old standards, and here it is, USASI Y14.5-1966. And then I went in there and took some screen captures of it. But here's the basis of the projected tolerance zone. Look how this tilted and causes problems. And then they have a write-up of why it has to be put in there. And then they actually said, oh, here's what the drawing call-out should be, is do this, 375, 24, 4 holes, position 10, diameter, tolerance zone projected 500. Like, not only did they know about the problem, they have a solution documented that we still use today. I mean, it's incredible. So like sometimes I'm embarrassed if some of these, people who designed this a long time ago, like, oh, you must be like having flying cars and stuff. And it's like, no, I mean, not quite. Like, well, what have y'all been doing for like 60 years? Oh, we made it as a Circle P. We did a Circle P modifier. But really, it is, what's the saying? You're standing on the shoulders of giants, and
it is, yeah.
That's what makes you feel so tall, and that's it. I mean, really, a lot of this stuff, that's what's so fun to teach. It's just basic engineering concepts that they documented for us, and we just get to add to it. Really cool.
Yep. And that's the whole beauty of it. That's the whole beauty of it, because if you didn't have that, then you would only be able to make what you can think of and invent, if you will, and describe by yourself. Whereas with this, you're getting the knowledge, you're getting the benefit of all of those people that came before you, right? It's like a multiplier to your own skill and potential. And
yeah, that's right. You don't have to write your note. You don't have to explain it to somebody on the phone and write emails. Oh, I wanted at this projected height, not here, and I want it to be there's a baked in set of symbols ready for you to use. That's what's so cool. It's an amazing language designed by engineers for engineers to communicate what is the worst case that you would accept. And as a design engineer, you can't be in 50 places at one time. You can't be in this place where they're making your part in there and make sure you do this and make sure that. I can't like hang over your shoulders every time. So I have a drawing that specs out, these are my absolute limits. It's beyond that, I won't accept it. If it's within, yeah, we'll buy that part. So really it helps as you're starting to scale or creating more complex parts with a lot of different suppliers and a lot of different manufacturers.
Love this comment. Very cool. Haven't seen the P modifier before, but I can see how useful it is.
Yeah, this I wanted to point out the standard again. This is Y14.5-2018 here. And remember all these formulas that I'm teaching, they're in the non-mandatory appendix here. And they have them just a little bit. I mean, the same formula is just different variables and stuff. But this is B-3. This is the floating fastener case. And they explain the formula as T equals H minus F. So the tolerance is equal to hole minus fastener. So smallest hole, biggest pin. And so you give the tolerance to each part. Now, this is the fixed fastener case when the projected tolerance zone is used. So when you use the projected tolerance zone, it's a very easy formula. The tolerance is equal to H minus F divided by 2. Now, they're doing a 50-50 split. So notice, divide by 2. So just 50% goes to the hole, 50 goes to the threaded hole. I do it as a 60-40, so you can really split it any way you like. But look how easy that formula is. It's just the tolerance equals H minus F and split it. Well, they do have another paragraph, B-5, and that is the extra provision for the tilting of the axis of the center plane. So it says when an orientation tolerance or the projected tolerance system is not used, then it's required to select a position tolerance combination that compensates for the allowable tilting of the axis. And that's that extra little formula that or provision, I guess is what they call it, that I was talking about, 1 plus 2B over D. And I was like, yeah, why should we use a projected tolerance zone if we could just, reduce the tolerance a little bit? And I was like, all right, reduce the tolerance a little bit. But what if P equals D, like my example, and then it became, if you plug in P equals D, T2 becomes a 3 times multiplier. I'm like, oh my gosh, 3 times the tolerance? I can't account for that type of reduction in tolerance.
Yep.
So it was like, use the projected tolerance zone modifier. Like that just proved it to me. I'm like, yeah, this is not a good formula, not using this. Make this simple on everybody. So it is a very clever fix. So yeah, looking at the calculations here, what would you rather have? A position tolerance of 17 projected out the correct height? Or would you have a tighten up tolerance down to a third of what you originally have? And wow, that's a no-brainer.
Yep. And we have a comment here from Ben 10, basically. And he says that these tolerances ensure we get the correct function, and it's a nice note, because using these tolerances you get the correct function. If you tighten up the normal tolerances, you get parts that will always function when put together. But what did you also get? You also got a more expensive production, right? So yeah, I mean, super useful. Let's just check that the thing works. If it works, don't mess with it.
Yeah, the like when you're just doing like holes and pins, let me just draw one real quick. But let's just say you have some holes in the top part, and you got your cross-section view here.
Yeah.
There's your clearance holes, and then you have your pins in the bottom part. It looks like this. How do I make sure that these holes will not be off position too much where they accept the pins? And it's real easy. Smallest hole, biggest pin. And then when you do your position tolerances, we say the tolerance zone always applies the length of the feature. So you get a cylindrical tolerance zone on this one, you get a cylindrical tolerance zone on this one. Now, when you insert that pin into the hole, the tolerance zones overlap each other. So it's just a really easy smallest hole, biggest pin, split it between the parts. It's simple. The problem is when you go with a threaded hole, you're actually not tolerancing the thing that you care about. When I'm positioning, the hole doesn't mate with the hole. It's the bolt that goes into the hole. So you don't want the tolerance zone to be the length of the feature like it normally is. You want the tolerance zone to be projected out where the bolt is going to be. And that way, when I put these two parts and make them in the CAD, then the tolerance zone will overlap with the tolerance zone, and you're back to a really easy smallest hole, biggest pin calculation. So it's like you're ghosting in a part that's not there and then tolerancing it, because that's what matters. And it
Which
just
is,
makes
yeah, exactly, which is what matters. It's the part that's going to do the work.
That's it. I'm just like, man, that's so clever. That's so clever.
Yeah.
1966.
It is.
That was a published standard that we still use today. It's really awesome.
Do you have any recommended reading for our people in the chat that would be readily available at their local bookstore or Amazon or something like that?
Well, my book would be one of them. Yeah, so that would be the GeoTol Pro 2020 would explain all that. So that would be one place for it.
There you go.
Also, the source, the Y14.5 standard, that would be another place.
Yeah.
Standard is a bit on the dry side. It's, cuts right to, it's standard speak. So when you do standard speak, you have to make sure that you use the exact wording that cannot be interpreted any other way. My book is an interpretation of the standard. How would you use it? How would you apply it? But they kind of stick to like, this is the definition of the symbol and that's it. A little bit of guidance, but yeah, trying to explain it in more examples is what I would have in my book.
Yeah. Lots of written examples. This was a big boon to my training when I took some GeoTol classes.
Yeah, the standard will always tell you what to do, right? Or it'll always tell you what. It very rarely tells you why, which is the example that Scott just gave us, and I think it's pretty eye-opening, isn't it?
Yeah, I kind of tell people the standard, learning from the standard is like trying to learn English from the dictionary. It's like, it's a great resource, right? Like go to the dictionary and definition of words, you need that, but you can't learn that way. You need like somebody to teach it to you in a more logical order with examples that make sense. And then, okay, now I need to go read the standard. Obviously, you need to know what a noun is and a verb is and an adjective and how the sentence is. But let's just start speaking, right? Let's just talk. Give me examples and practice with it.
Yep, very true. Very good analogy, actually.
There are so many interesting questions in the chat right now. I want to get to some of them. How are the projected tolerance zone height and counterbore depth determined for socket head cap screws, which I think we covered pretty well, but there could be some nuance there.
Yeah, that's a good question. You actually have to do two fixed fastener formulas. So you do fixed fastener formula for the clearance hole, and you do hole minus fastener, and then split it between your tapped hole and clearance hole. And then you have to do another one for your counterbore and the counterbore to the head. So how much room you got between the counterbore and the head. Usually that's a little bigger, but sometimes socket heads can be a little tighter if you want it to look really nice or something. Then you got to do a formula in that one. So then, just do it again.
Can you do MMC with a projected tolerance zone? And if so, how would that work? Does it seem like having bonus tolerance would make sense since you wouldn't know the size of the mating part?
I don't put MMC modifier on threads. You're going to make me wade into a controversy there. Yeah. There are pictures like that in the standard. They put MMC on a threaded holes axis. Doesn't make any sense to me. How do you get bonus tolerance from a thread? The pitch axis gets bigger and then it can shift more. I don't think that makes sense to me. So I don't put MMC on that. I don't think it makes sense. I just keep it, hey, let's keep this simple, 17th thou regardless. And I think it's because you don't know what size the pitch axis is. It's really hard to measure the size of it and get the bonus out of it. So I say keep it simple. Just use an RFS on those.
Perfect. I like this one. Totally, GD&T applied correctly should reduce costs and not increase them. He's replying to someone. So I've heard that there's some suppliers that have this reputation. They see GDT and say, we got to raise the price. But I feel like some of that is also if they can't read GDT very well. Did you have any thoughts on suppliers pricing for GDT?
Yeah, geometric tolerancing, it's the exact opposite of that. The purpose of it is to give more manufacturing tolerance. Literally, that was why it was invented. We're getting way too tight on plus or minus. We cannot hold plus or minus any tighter than plus or minus whatever we put. So we need a system that says, all right, if this happens, then that happens. If this happens, then that's happened. So it's a way to look at X, Y, angles, the size all together is, will this work or not? That's how we judge parts, whether they function or not, and not just blindly holding somebody to a plus or minus tolerance because somebody said they could hold that.
Absolutely. there's a lot of chat conversation on that, but this is great. I saw one. There it is. I think part of the problem dimensioning is where you need a CMM to measure, and a lot of smaller machine shops still don't have that capability, unfortunately. Do CMMs take a lot of influence in the inspection process?
Oh, you wouldn't need a CMM for something like this. This is such a simple geometry. This would be very easy, angle plate with a basic height gauge there. So you'd set up the angle plate, set up A, set up B. You'd have probably a gauge block over here for setting up your C, and then measure the hole in the Y direction, rotate, measure in the X direction, and then make sure that combination of X, Y, like Costas was saying earlier with the Pythagorean theorem, it still lies within that tolerance zone. So yeah, remember, geometric tolerancing was around way earlier than CMMs were. Geometric tolerancing invented in the 1950s, 1960s. First CMM was like, 1970s, 1980s or something. And that was like the one CMM in the world, and even CMMs haven't hit widespread use until the 90s and later than that. So yeah, this is a system to work out worst case, and it's better than plus and minus. Now, as your part gets more complicated, you just get more complicated compound angles and crazy stuff. Yeah, CMM is going to help, but it's not because of geometric tolerancing. It's because of your complex geometry.
Sometimes it's hard to remember that a very, very, very mass majority of these standards were written before computers existed. People were doing these pen and paper.
Yeah, and
that's really, guys, that would really impress the original founders of geometric tolerancing. I mean, if you showed them a CMM, they'd just be like, knock their socks off. It's just like,
exactly.
You mean I can measure anything to anything? It's like, yeah, literally anything. Like set up a datum reference frame and measure 3D space and make sure it lies in the geometry. It just blow their mind. It absolutely.
And we're talking about CMMs. Like, imagine a passive arm. Like, I mean, I don't want to mention companies, but there's one prominent company that did it first, and people know it by that name. And it's just a robotic arm with no motors, and you touch it, and it measures 6 degrees of freedom, and you get a point in space. And come on,
articulating arms are unreal. They're and all the companies, all the major inspection companies have.
Yeah, everybody does that. Yeah,
they're unreal. It just really is just measure anything to anything, and you can do it so much faster. It's just like manual machining to CNC, and then manual drafting to CAD systems, and it's plus minus to geometric tolerancing. As you get more precise and more complicated, just that old style just won't work anymore. And so it's like, yeah, you can live down there in the gutter and use plus and minus tolerancing for a while, but after a while, it's going to be like, get on my level, right? Get on my level. We need to talk about some complex stuff here. And plus minus doesn't have the ability to talk about this complex stuff like geometric tolerancing does.
And can I just comment on one more thing on the CMM? It's the same thing in the machining space, right? And let's make that with a CNC. Well, yeah, sure, CNC machines are great. I mean, they're awesome. They're not just great, but let's not forget, guys, that back in the 60s that we were discussing earlier, we went to the actual moon, and most of that. Those parts were made on conventional machines, and to that point, just take a look at the sealing and clamping mechanism of the door of the moon module. Not the entire module, just the sealing mechanism of that door, right? And these were all individual parts made on conventional machines and measured with a decent granite plate and a height gauge, which is what I wanted to say earlier. So yeah, sure, there are ways to make your job slightly faster, but it's not impossible if you don't have these means.
I like this. Plus or minus is so square. This is Dad's joke. But position on threaded holes is hard to measure. Is there any best practices for working with position on threads?
Yeah, you probably use thread gauges. So thread gauges are like little things that you can put in there, and then they have like a little stalk or diameter that sticks up, and that would be ground on the center of the pitch. And so then you can thread those into the hole, and now you got this really nice precision diameter you can touch off of. Think about that for projected tolerance zone too. You're threading that thing in there, and then what's sticking out is your awesome little ground diameter on the pitch, so you can measure that. Now, the only thing with those is they can be a little sloppy, right? They can kind of rattle around in there a little bit. So some of them have slits put into them, and then the slits are constantly trying to expand it in there. So then when you put it in there, that kind of expands, because it's got the slit into it. And so then it takes out the slop, and now you just got pretty much centered up on the pitch. Like, that's the axis that you care about.
Message for you, Scott, just came in. Totally worth showing here. Scott, grateful for your outstanding contributions to the GD&T community and for making this complex subject accessible to engineers around the world, and your work continues to inspire and educate us all.
Oh, that's great to hear. Yeah. Like I said, I can't take all the credit for it. I'm teaching all the stuff that those old engineers did, but trying to make it exciting because they did such a great job of documenting it for us. So I like to keep spreading their good word and their ideas, and trying to, of course, advance the subject forward too. So yeah, I appreciate that.
Yep. Absolutely. Let me know if I've missed anything in the chat, folks. But
I think we're caught up. Also, hello to our viewer in Germany, it looks like. We have one person speaking German. I hope you're getting some of the information still. Numbers are universal, right? So,
yeah. And most of the symbols that we use today are also universal. So,
yeah, it's really not much different here than ISO GPS, especially on this example. This example, ISO GPS, it's identical to this. Once you got a datum reference frame, cylindrical tolerance zones, there's very little difference in these. You really have to start splitting hairs before you start seeing the difference between ASME and GPS. So, it's pretty nice.
We had a quick Libre question come in. I'll take that one real quick. It was asked, can we do basic dimensions in Libre? Adam answered that really well, but I'll just say you just click change dimension, tolerance, and basic to supplement everything. Adam's answer to get that.
Can you mass change them all at once, or do you have to do them one at a time?
You could change the standard for the file. You could change your...
You can actually.
Yeah, so when you actually load in, you can set a new your default settings when you create your drawing, and it should stay.
But I think also if you shift select, some of the options remain available, and I think that's one of them. I'd have to check though.
Let's see, shifts. Got to get out of my dimension tool here. Shift select. Oh yes, that's true.
Yeah.
Cool. So if you're looking to do some of this in Libre, there's that. Or at least get your
Libre has really good GD&T. I find myself very often looking up first what I need to do and then going into a Libre and seeing that it already had it, especially in welding, right? That's where I found that. And I was like, oh, it already has that. Oh, so cool. It also has ANSI and metric symbols. Welding symbols are, there are more differences. Although if you look at them, you recognize what's what, but they are slightly different. Anyway, yep.
I wanted to point out too the standard different ways you can do basic dimensions. So let me just pop to this figure. So in Y14.5 said there's actually 4 different ways to identify basic dimensions. So remember, on round parts, it's sometimes better to do a bolt circle angle setup. Doing a polar coordinate system just far simpler to just do, hey, they're all in a bolt circle. This is a theoretical circle, right? Bolt circles aren't real. That's why we'll make it just a basic dimension with no tolerance. So ideally, they would love to be on a 26 millimeter bolt circle, 8x, 45 degrees apart. But that would be no different than if you did it in rectangular coordinates. Did it all like this. It means exactly the same thing. But yeah, on round parts, it's probably a little more efficient to do it this way. I would point this one out too. You don't always have to put boxes around them. This is a note that we'll sometimes put in the corner of the drawing. Untolerance dimensions are basic. So if I didn't put a plus minus on it, then it's considered to be a basic dimension per this note that you put on. And some people like that because then it just doesn't get all cluttery. You know, when you get all the boxes on everything, you know, this has a box and this has a box around it and this has a box around it. You know,
everybody gets a box.
Yeah. Yeah. But when you start using so much geometric balancing, then everything has a box.
Yeah.
So let's start doing cage-free
Well,
organic.
sometimes you've got so much stuff going crazy on the page that it seems dumb to get rid of just that little bit of extra stuff on the paper, but it would really help sometimes just to clear it up a little extra.
It is just actually clutter your eyes when you don't have so many lines on the page. It really can clean things up.
And actually, I have seen and worked with senior engineers that are of the disposition that the more stuff on the drawing, the higher level the drawing is, which it's not true, guys. It's not true. The stuff that you have on the drawing need to be there for a reason, right? Not to impress people, right? And also,
that is another step that putting all the dimensions in the model. And so a lot of companies are saying see CAD file for the basic dimensions. Yep. And so now you have a CAD file that has all the dimensions, and then just on the drawing you just put size and position.
That's a new fashion trend, I have to say. I don't like that.
Oh, you don't like
that? I don't like that. And I'll tell you why. Because I'm coming from having lived in both sides of this, in both sides of the paper of the drawing, right? The designer and the machinist. So if I have like that flange, right, I would never set up a CNC machine and go through CAM and to do that. No, that's a divider on a mill all day long. So what do I do then? Do I give the guy next to the conventional mill, the Bridgeport I bought in 1988, do I give him a laptop next to it? No, he needs a paper and he needs to have whatever he needs to make me that part, right? So I think that I've heard so many people say drawings are dead. No, they're not.
Yeah, and all of them are option. This one they added in the 2009 standard. In 2009,
I know.
More model-based definition friendly. And, simple little flange like this, probably would make sense to just have a 2D drawing for it. But as you get more complex, crazy machinings with holes all over the place, just putting XY dimensions on there can get very cluttery and cumbersome. So
for sure,
it's an option. I think the more complex your part gets, the more this can be helpful.
More options, exactly. More better.
Yeah. More options, more better. And can I just say for our Libre users that if you guys make a single hole and then do a circular pattern of it, you will get automatically the bolt circle showing in your drawing. That's just a CAD use thing, if you're so inclined. Whereas if you pop in the individual holes, you won't get you can still draw the bolt circle, but you won't get it automatically. Yep.
Good opinion question on this one, I think. For threaded holes, oh gosh, a comment came in and I think I just lost it. Here it is. For threaded holes, lost it again. There we go. We use position with MMC applied to the minor diameter, so then we can design functional gauges to inspect those holes with a solid pin. Can I get your opinion on that practice?
Ooh, another controversial one that you're making me wade into. I am very much a functional guy. If it's not functional, it doesn't belong on my drawing. So what I would ask you, is the minor diameter the functional thing, or are you just making a compromise to make it easy to inspect? And it sounds like you're making a compromise to make it easy to inspect. And so I'm going to put my functional need in here. I want my pitch diameter within 17 projected. Now, if somebody said, well, you need to make it easy to inspect so that I go off the minor diameter. Oh, but I don't care about the minor diameter. All right, fine, I'll do that. But I can't give you 17 anymore because the minor and the pitch might have a coaxiality problem. They might be off 2 thou. So if you force me to do a minor diameter check, then I'm going to reduce the tolerance down to 15. And no, don't reduce the tolerance if that's not functional. So what I'm going to do is put 17 on there. Now, a good quality engineer is going to look at that and say, ooh, I see you want 17 on the pitch, but I want to make a cheap gauge on the minor diameter. So I'm going to artificially guard band the tolerance myself. That's what I recommend quality do. You guard band artificially. So, all right, we're going to use a gauge for this. So we're going to bump it down to 15 thou and go off the minor diameter, and we still think we met your function. Cool, you do your thing, but I'm not changing my drawing because the next person wants to use the thread gauge and they want to do it properly. So I want to give them the full 17 possible. So what I say is that's a quality plan, and we guard band tolerances. In guard banding is where you artificially reduce the tolerance to protect your hard boundaries set by the drawing. So you're guard banding those tolerances, and cool, you do that for now. But then as soon as we get an upgraded CMM, then we're going to the full function. And then I don't have to go back to the design engineer and, hey, can we get that 17 back on the function again? Sorry, that ship has sailed. We're back at 15, So yeah, I really like to stay functional, and then quality, yeah, you do your thing.
Perfect.
Can I just also comment on that? And that's why, guys, engineers, we have a seal and we sign things, right? Because we make decisions and we bear the responsibility of those decisions. That's engineering, right? If you mess up, you messed up. There needs to be accountability. So if the quality engineer decides easier for me to do the minor, I'll just, bump the tolerance by 200s. Yep, you did that. You sign off on it, right? Let's not forget that.
Yeah, this happened to companies who would design parts, way back in the 80s and 90s, and it was kind of hard to measure off the pitch. So they would reduce the tolerances to accommodate the current inspection methods. But all of a sudden, this drawing that's been now it still works today, but we're still stuck on those old quality methods when we've got these amazing tools that can measure right down to the nth degree and measure it properly. So yeah, don't hide the measurement deficiencies by, compromising your product definition.
Got it. Interesting question here. An intern in the oil and gas services is in quality control. They only have to cross-check standards and nothing else. Do you see a lot of market demand with people who are really good at cross-checking standards, or?
Maybe I'm not quite understanding the question. Yeah. And so,
I'm thinking what they're saying is, if you have an intern working at a company and their primary responsibility is cross-checking the standards and pretty much nothing else, is there a lot of market demand for something like that?
Well, all I can say is for geometric tolerancing standards, that's what I focus on. But there's a lot of other critical standards out there in industries too, oil and gas and pressure vessel standards and codes and stuff for those too. And yeah, those are hard to read. Those are hard to read standards and which references what. And there are standards experts. That's their expertise, is knowing, which standards apply. And it's almost like, navigating, the government codes and government laws and stuff like that. It's nice to have an expert on hand that knows how to navigate through those to get their job done.
Gotcha. From an earlier question, thanks, Scott. That was the answer I was expecting. Just wanted to hear it from the expert. Great discussion in here. So we're grateful to have you.
Yep.
Well, do you want to maybe talk about the composite position? That was kind of the next level. I don't know if people want to go to that next level or not, but
I think two thumbs up.
I do.
Okay. Yeah. So this is a quick formula that we can use, but I want to show another technique we use for kind of a little bit more advanced techniques. And composite position, that's what I'll kind of talk about, more of the basic level of it. I don't want to go too deep into it because, boy, you could get really deep into this one too. But this is where you can have two position tolerances for a set of holes. And that's usually where you have like a larger location tolerance relative to your datum reference frame. And then you have a tighter one that's more hole to hole. So I tried to keep kind of the same parts so that you kind of have the same idea of it. You have a back face A, bottom edge B, C, and basic dimensions. The upper one reads just like a normal position tolerance. That's a position tolerance of 0.6 to the datums. And then you can do a lower spec that controls the holes, just hole to hole. In ASME, 4X is a grouping mechanism. It's a pattern creation tool. And so that position tolerance on the lower segment is going to be applying between the features in the pattern. They have names for them. These are not my favorite names, but they called the upper one the pattern locating tolerance zone framework, or the PLOTSIF. and it locates the pattern relative to the datums. And then the lower one is the feature relating tolerance zone framework, or the Fritz-if. So they say the Fritz-if may skew, rotate, or displace within the plots-if. Not my favorite way to explain it, but that's what the standard says. The way I teach it is this is just relative to the datums. That's what this reference is here. You want it positioned relative to what? Well, relative to the ABC datums. And this one is just going to be relative to each other. And then the A in there is just an extra thing that also controls perpendicularity to A, which is common to have that additional spec on the bottom to perpendicular A. Okay, so let me show just a couple of animations for that one here. And so I like PowerPoint animations. I think, okay, there's a static picture, kind of get it, but let's show it here. Now, I had to greatly exaggerate this because a diameter of 0.6 millimeters on the screen would be like the size of, pencil lead in your mechanical pencil. So I have to greatly exaggerate this. But these are these oversized bullseyes that the axes have to lie within. That's the diameter 0.6. And I want to show the upper one reads just like a normal position tolerance. Location to the datums, ABC. Now the lower one creates another set of tolerance zones. And this is a position within a diameter of 0.2, and that's going to be relative to each other. And then also relative to A, so you have to think, what is A? A is our plane that we're looking normal to. So the cylinders are popping out of the screen at you relative to A. Now, because these smaller zones of 0.2 don't have any reference to BC, they're unconstrained. They're allowed to float, but they have to float as a pattern. So the group of tolerance zones, this is not the holes, this is the tolerance zones that I'm showing, positioned cylinders of 0.2 are allowed to float around. So you could have them shift left and right. They can float up and down, or even diagonal, and even skew like this. So you're specifying a set of tolerance zones of 0.6 locked into the datums, and you're specifying they also have to meet a set of tolerance zones that are 0.2 in size relative just to each other. So the cause and effect on this one is it allows our whole pattern to float like this. Yeah, that's fine. Float like that. That's cool too. I'm okay with this. Don't do that. Oh, don't do that. That would be bad. So I can have them do like kind of this and this and this, but I can't have one hole go this way and one hole go that way, because then the part won't bolt up. So where would we use something like this? And this is common. It's a specialty application. Not all parts would need this, but let's say you have a gigantic panel for something, and you got your B datum on the side and like a C down here, and then you got this 4-hole pattern like way up here in the corner like this. And I just go to my hole and I say 4x, we got your diameter, and you just do your fixed fastener formula, right? Position tolerance within a diameter, 0.2 at MMC relative to the datums, because you did your fixed fastener formula, you listened to this podcast. But then manufacturing comes back and says, well, I can't hold that 0.2 relative to those datums. Do you see how far those datums are? They're like, 3 meters off to the side like that. Oh, well, can I get some more tolerance? And you're like, no, I can't give you more tolerance. The fixed fastener formula says I get 0.2. But then you remember, actually, I don't really need 0.2 relative to those datums. I just need 0.2 hole to hole. So the red one turns into the yellow one. And then we give a bigger position relative to the datums. And this is just some big number, some big tolerance. I don't know, 0.6, 0.8, 1 millimeter. What can you hold relative to datum? Something very large. So it allows that little component to float around a lot. But then this is the hole to hole to each other. And that's your formula. And that's going to be, whether it's your fixed or your floating there. So it's an optimization trick. And that's what I teach people. If manufacturing is good with the red one, oh yeah, good with that one, right? 0.2 relative to the datums, fixed fastener formula. But then you've got this one in your back pocket. It's usually for larger structures like big weldments or chassis or housings or something where you have a lot of components mounting on there, and they can kind of float and do their own thing as long as this better bolt up and that better bolt up and that better bolt up, but they can kind of shift off of your global reference frame a lot more.
So cool. This is so cool. I love it.
Yeah, and it's funny. I had a couple people, talking about plus minus, and oh man, how is this better than plus minus? And actually, let me just do, if don't mind me just going off script and talking a little bit, but gosh, the old days we used to use plus minus. Let's just say we had a simple plate, and you have 3 holes in it, and these 3 holes, they have a size of, I don't know, 10 millimeters or something, plus or minus 0.1. And then we give a dimension between those holes, and let's say we want it to be 25 millimeters from here to here. And so then we put a plus or minus 0.1 on that size, or on that dimension right there. Now, how do we dimension out the 3rd hole to get the least amount of stack up? Or they said, oh, don't use that GD&T stuff, only plus or minus. So how do we dimension out the 3rd hole to get the least amount of stack up? Dimension it from the first hole or dimension it from the middle hole?
From the first hole, so you don't get a stack up.
Yeah, so you don't get a stack up. So then you would give this distance is 50, and you'd say plus or minus 0.1. And that would be to here. Okay, so then you hold the distance between the first 2 holes is plus or minus 0.1. Between the first and the third is plus or minus 0.1. But what would be the possible distance between the second and the third?
+2. Plus minus 2.
Plus or minus 0.2. That's a stack up, because if this one shifts 0.1 to the left, that one shifts 0.1 to the right, you'd have a plus 0.2 or minus 0.2.
You end up with the same problem no matter where you end up dimension.
Given this dimension here, what you should have done is given 25 here and did plus or minus 0.1. Now, when you do it this way, now you hold these 2 as plus or minus 0.1, and you hold these 2 as plus or minus 0.1. Well, wait a minute. What's the possible distance between the first and the third?
Yep.
There you go. Same thing. Plus or minus to 0.2.
So then people say, oh, no problem. Why don't we just do all 3 of them? Can you do that?
No. Yeah, well, no, actually.
It's like drafting 101. It was like the worst thing you ever do in your drafting class. That's double dimension. Yep. You can't do that.
Yeah.
So, but we don't.
You'll fail the course if you do that
anymore. You make these basic. We don't tolerance dimensions. That's silly. They're theoretical things. So just 25-25 or 25-50. It doesn't matter. Just pick 2 and stick with it. And then you take all the tolerances off of this and use 2 out of the 3 to define the true perfect position. And then you go straight to the holes and you say these holes have a position tolerance, and you say diameter of 0.1. So now right on that perfect position, you have a cylinder of 0.1, a cylinder of 0.1, a cylinder of 0.1. Now, how much can the left diameter be off to the left?
0.05.
0.05? This one can shift to the right, 0.05, plus 0.1, minus 0.1. Between these 2 holes, plus 0.1, minus 0.1. Between first and third, plus 0.1, minus 0.1. You had 100 more holes, and it's still plus minus 0.1 between 2 holes. It's amazing. You don't tolerance the dimensions. That's what gets you in trouble. You tolerance the features and say these 3 features have to be located within 0.1. Now, remember, to the edges really didn't matter. And so what we used to do is we used to say the dimension to the edge, used to say, oh, yeah, that's 20 millimeters. And I don't really care to the edge. So then you give like a plus or minus 0.4 or something. We didn't really care. Now, in the up and down direction, we didn't really care either. So we would give this distance as, let's say 20 millimeters, and then we'd say plus or minus 0.4. Now, if we take the position tolerance off for a second, go back to plus or minus world, what does that mean, 20 plus or minus 0.4? Does that mean that hole can go up 0.4 and that hole could go down 0.4? Or does that mean they have to
doesn't it?
Together plus or minus 0.4?
Well, you're not specifying the horizontal ness of it like you would in CAD, actually. I'm guessing, one can go up and one can go down.
Okay, what if I put a 3x on there? Now, are they together or separate?
Now you're testing my... I would say that now... Well, I would perceive it as they being a set now, yeah.
Nobody knows the answer to this. You see, and I perceive it as that's all we got. This is my assumption that I have. So you go consult the standard, like, what does the dimensioning and tolerancing standard say about that? And the standard says, you're on your own, buddy. You're using a plus minus system that's unstandardizable. So that's why it's like, no, we don't do this anymore. We don't tolerance the dimensions. We make it all basic.
Very true.
no tolerance. And then we go directly to the hole and we give the full set of instructions to the hole. And that's what I've been teaching this class here. Position within a diameter of 0.8 relative to A, B, and C. So that's going to be the location relative to the datums, and then you'll properly label the datums. This is your B and
Oh yeah, for sure. Yeah.
C. So now it's like, no doubt, you got a location on the holes of plus minus 0.4 relative to the datums, and then a tighter position between the holes. So it's like, yeah, this is what we've evolved from, right? We're getting rid of the plus and minus because it doesn't make a lot of sense, and moving towards a more explicit tolerancing system that's on the holes, on the features. Way better.
This Jason Reen says, I admit I didn't quite follow the why is GDT better than plus minus discussion earlier. This explanation going on right now, I feel like I finally understand. So this is a great thing to go off script with.
Oh, good.
Oh yeah, for sure.
Oh man, it's so much more than like square tolerance zone versus round ones. That's how it gets sold to people. They're like, well, plus minus creates a square zone, this creates a round zone. It's like, yeah, that's cool. But look at all this other cool stuff you can say. And we haven't even gotten into how cool the datum reference frame can be. Yeah. This is just really easy datum, B edge, C edge, right? But holes and slots and dowel pins and alignment holes and much cooler datum features you can have on real parts.
Yep. And this is OmniCube made a joke about square dimensions, and this is where it makes sense because plus or minus gives you a square or a rectangle and pretty much nothing else. So
and that's it. This 2D square, I think that's a good way to say it too. 2D square, because are you controlling it in 3D? Is that the front of the hole, the back of the hole? Is it both? Nobody really knows for sure. It's just kind of like, you know what I mean, right?
Yeah.
I love this. Brian Hunter, love this. The presenter is fabulous. I haven't done this stuff to this degree since the late 60s when designing satellite mirror supports. Great refresher.
Oh, man.
It up. Cool. And Brian's a cool guy because he joined our last live stream on his I think 60th anniversary, somewhere in there. So
55th, if I remember correctly. So a legend all round, Brian.
Yep. Happy anniversary.
Yep. And can I just go back to a thing that was said earlier in the stream that some machine shops will just automatically quote you a bit more if they see GD&T on the piece of paper. That's good, because if they do, they don't know what they're looking at, so don't work with them.
Yeah,
I'm very sorry to say, right?
Yeah,
but
I think that's a good comment. Yeah, at some point, get on my level here. No,
it's really because I'm actually giving you more freedom to work with. I am making your life easier, right? But you don't know that. Yeah. So if you don't know that, what else don't you know? I mean, it's a harsh way to think about doing business, but I'm going off of the potential license that I get by working on both ends here. No, you need to be on your game at the very least. If you see these symbols and you don't know what they are, I mean, you have a flip open a book and read up, but Google it.
Well, it's crazy as well, Costas, because like I was saying at the beginning of the stream, this is something that I have zero experience in whatsoever, and I've already learned the absolute basics. And obviously, the world of GD&T is absolutely massive, and this is a bird's eye view from 1,000 feet up.
It's a universe.
But I've learned the absolute basics and can look at this and understand what I'm looking at with the past hour and a half of learning from this fantastic presentation, and I can already understand the basics of it. So if your machine shop is saying they don't know what they're looking at, that's a problem.
Yes, it is.
Yeah, and it's a lot easier to read GD&T than it is to create GD&T, and it's kind of like with Spanish with me, if someone speaks slowly and uses simple words, I can kind of understand what you're saying to me. But, to speak Spanish, I'm terrible. I mix up the conjugations. I'm not so good on that, but it's a lot easier to read than it is to create. So design people, you need to be a little more involved in learning and how to put it on. But yeah, to read it, I think there's no excuse. Yeah, look it up. There's symbols here. Look it up in the book. Position tolerance. There's some great examples, and cylindrical tolerance zones. Once you understand it, you're like, why would you ever go back to plus or minus? It really is that way. Like, why would you ever do it the other way then? For a better system.
We have a question here. I really appreciate the insights you're giving. One quick question. Can you please explain what's the key difference between composite and multi-segment? That's a good question.
Oh, boy, that is a good question and a long one. So it could be a long answer to that one. And gosh, I can give you the short answer, but then it's going to be like, what the heck does that mean? But yeah, composite and two single segments, they don't really start being different until you start adding like additional datum features in here. But very quickly, I'll put in red here, the lower segment refines location between features in the pattern. So between features, like we were talking about, but constrains in rotation only. So it only controls perpendicularity, parallelism to the lower segment. And then if you do it in two single segments, then it's a regular position tolerance. So it constrains in translation and rotation. And it's like a little more involved there. So that one would be probably like a whole another hour to talk about it. And also it's different in ASME and ISO too, which is why I didn't want to get into too much of the muddy water and the differences between ASME and ISO.
But I just to confuse everybody even further, if you understand that, if you look it up and you understand why that happens, you will also understand why in most parametric CAD systems, you add constraints which feel natural and logical to you, and then the system tells you, I cannot do that because you just over-constrained your part. So that's the difference there, right?
Yeah, that's right. The datum reference frame is really all about constraints. And that's a great
training degrees of freedom. It's like you're taking that cylinder and you're moving it around, right? That's how I look at it.
I would say in most cases,
high level,
want to lock it in, lock it into your datums. And then there's these situations where you say, oh, I don't want it locked in the datums. I have a tighter requirement between and looser to the datums.
One question that I think I missed is I read in the 2018 standard, I guess we're no longer allowed to put plus minus tolerance along with position tolerance. I believe that's correct.
Yeah, and size tolerance, of course, that's still good to go. Of course, we'd always use a plus or minus on the size, but you're right on the dimensions here. These have to be basic, and that is a requirement with position tolerances. You must define the true position with basic dimensions, and size tolerance, of course, you have to have a plus minus, but yeah, all the holes, all the dimensions locating the holes would have to be basic.
Yeah,
and that's been like that since 1982, actually. So yeah, 1982 is when they first said, hey, you should use basic dimensions here. Stop screwing around with that plus minus tolerance.
Yeah, but if you use both, it's a nightmare, isn't it?
Oh, yeah.
To actually check whether you're in spec or not.
Yeah, people think GD&T is in addition to plus or minus, but no, it's a replacement of plus or minus. Like position and profile replaces plus or minus. It's the successor to the older system.
Yeah, exactly. Well, I think this was one of the better streams that we've done.
Yeah, probably the best, actually.
Yeah.
Yeah, very fun subject. I get very excited about it. Some people are like, oh man, how could you get excited about geometric tolerancing? It's cool. It is like, I don't know, it's such a great combination of like physics and math and philosophy and language, like all mixed together to, communicate and control really cool engineering concepts. I love it.
It is cool.
Yeah, philosophy as well, because you are actually tolerancing a different thing. Yeah, you're going one level up.
It's a feature-based tolerancing system rather than
exactly.
Tolerancing. And that's like, oh boy, you got to wrap your brain around that.
That's a very good observation there. Yeah, I like it.
I've got two Libre questions. I'll just knock those out real quick. So I love this one. It is. The dimensions in CAD is interesting. What CAD software supports this right now? Well, I can tell you a Libre does. We have future control frames that we can insert here and, add leader lines and things. and start building. Maybe I can go with our position is always my favorite, I think. But yeah, so we can start just building out these feature control frames just like we've seen in some of these demonstrations here. So
Those
anyway,
drop downs are dynamic.
Yes, they
Yeah,
are.
there's all the check boxes and pull down menus for all the symbols and stuff. That's great.
Yeah, we have
What
composite
I like
frames
about that
and all
too
that.
is you don't have to like just start from scratch. Like, what does this symbol look like? It gives you options of what you can do in different places. It really acts like a really great guide to help you apply it. You know, it won't let you put, you know, a funny symbol on this, you know, a diameter symbol on that when you can't or something like that. So, you know, what we had to do
There's a
before
lot.
and draw everything, you had to think about what symbol do I put? How does this box look? And it gives you all the options, like just ready to populate them. That's really nice.
Absolutely. This is a very interesting one. I'm a fan of numbering dimensions on drawings. So if you need to track, report measurements, you have the reference to the drawing. Is there an easy way to number all the dimensions in a Libre? I don't believe we have a native purpose-built feature that would sequentially and autonomously provide numbers. We can, of course, come over here and add numbers above or below, which you probably already know. So that's an option. But if you'd like to see that, please go to the home screen, submit a request for a new feature. I'd love to have that documented because I love that idea as well.
Oh, OmniCube just made a very, very important comment here, right? And let me just start by saying most CAD systems in their drawing template, they have a disclaimer, let's call it that, if unless otherwise specified, all dimensions are plus or minus this or that, and good reminder, right? If you are using positional GD&T intolerancing and all that, it does supersede the plus or minus, right? Of course, most do actually say unless otherwise specified, but it's always a good reminder to actually say that. Yep.
Fantastic. Well, are we? Do we want to do a giveaway time now, or?
Oh yeah.
All right. What's a good hashtag, guys?
Hashtag GD&T.
I like that. GD&T. Hopefully everybody can type ampersands. Well, get a text block for that.
I mean, come on, it's Shift 7 in my keyboard.
It would be the same in the US, so
Should be. Well, you know what? I'll throw my hat in.
Yeah, for the very, very rare occasion where a couple of the presenters here are also going to throw our hat in the ring here, because this is extremely valuable stuff.
Yeah.
Bill Black Taco Friday.
Bill Black, yeah. Well, Bill, you know that hashtag always wins, but maybe not the prize that we are giving away today.
Yeah. So hashtag all caps GD&T in the chat, and we'll see what happens here. Give a few minutes for the chats to come in.
Yep.
Loving it, GD&T.
GD&T across the board, man.
Still see them coming in here. This is great. Hashtag GD&T. So we're giving away 3 seats. So we're going to be doing this raffle 3 times. And then feel free to email joseph@alibre.com when if you win, and we'll get you set up here.
Bill Black.
A few more minutes here for... Bill Black waited till the end so no one was distracted earlier.
Well, I am thinking about food now.
Yep, Taco Friday.
Yeah, because we are a bit ahead in terms of time zone over here, so it's about that time.
All right, I think that's been enough time. Let's try a lottery here. Here we go. First winner. Jason Reen. Wow.
All right.
That's one lucky
Go,
guy.
Jason. Go, Jason.
Good job, Jason Reen.
Go, Jason.
Yeah, Jason participates in so many of our live streams. We're really grateful. And moving on to a new job, I hear. So congratulations on the new direction, Jason. Let's try another one here. Jason Rain, send me an email.
OmniCube, this is for seats for the webinar by GeoTol, not for seats of a Libre.
All right, congratulations. I don't know how to say that, but send me an email, joseph@libre.com. Again, I'll change the text block here to my email.
Yeah, this is a seat to our GD&T training course. We have a longer GeoTol training course that covers 6 units. It's about 16 hours of training that just teaches you the basics of geometric tolerancing.
Lots of invaluable
That is very
material.
cool.
Oh,
Very
yeah.
cool.
Scott, we'll go back to your screen. If you want to pull up some information about this course, I think probably a lot of people want to sign on as well if they don't get the lottery here. We got one more. So let's do one more raffle, and let's see some more about this course as well. So here we go.
Yeah, this is our core concepts course that just, what I think the basics of what people need to cover. There is a more advanced specialty concepts one that goes into more details on the specialty, but just get up and running with the basic intermediate course. Yeah, our GD&T core concepts is great. So it's like online videos, so it has videos and then interactive quizzes and stuff that you have to go through, and it teaches you what you need to know, the datum reference frame, all the constraints, position, profile, perpendicularity, all the great symbols you need.
That's great. It's a great
Outer
course.
surface, I see there, outer surface.
Profile, boy, that was another great topic
Profile,
I could have gone into. Profile is so cool. That's actually my favorite symbol, but position I like the calculations too, so I like that one. But position and profile by far our most common and important symbol. But profile,
very important.
I want to hammer quite a bit in that basic class as well, because what a great thing to eliminate, again, a lot of the stack up issues that you get from plus minus tolerancing. Let's make the dimensions basic and use a profile tolerance way better.
Yep.
And,
by the way, the last winner was Spamioso. We didn't acknowledge that, but we all saw it. So,
congrats,
Spamioso. Just spam Joseph with emails.
I'm open for it. So yes, can we purchase the course? If so, how? That's probably an important one to cover if that hasn't been answered already. Yeah,
this one.
Thanks, Adam.
Yeah, they're both of these courses can be found on our website there at geotol.com. And so the GD&T core concept, kind of a more basic, start, intermediate. Also, it goes kind of basic, intermediate, and then the specialty concepts would be like all like kind of the weird stuff, composite positions, definitely more of a specialty concept. But on our website there at geotol.com. And it's written to ASME Y14.5, but we also have some comparison section to ISO GPS. ISO and ASME are so similar to each other that you can kind of use the same concept, teach the same thing, and then just show you, here's a few little differences that they do. Yeah,
this is just the tip of the iceberg of the kinds of benefits and knowledge that you can get for geometric dimensioning and tolerancing. So if you enjoyed the stream, this course is going to go the under part of the iceberg and learn a lot of cool core concepts. I've taken these classes actually a few times earlier in my career before I was at Libre, and they just totally changed the way that I look at GD&T even after I learned about it at university. So I really recommend these courses a lot.
Okay.
And I like the background on that slide, the crankshafts.
Yeah.
Although I'm trying to count crank pins. Is that an inline 6? Looks like an inline 6. Anyway,
it does kind of look like that, doesn't it?
Yeah, it does kind of look like that.
2JZ.
2JZ. There you go. RB26.
Yeah.
I'm more of a Nissan guy.
Absolutely. Well, Jason Reen may not be able to join us for live streams anymore, so there's going to have to be another lucky duck to take his place. But we're grateful for you, Jason, and good luck on your new job.
Well, Jason, you can always catch them on the replay on YouTube. and you can be sure that if you ask anything on the forums, we'll be on it and we'll try to help to the best of our abilities, as we always do. So yeah, you won't be able to win any more stuff, but
Like and subscribe.
yep, like and subscribe, guys.
Yeah. So where else can we find you, Scott? I know that I've seen the GeoTol YouTube channel. I think you're other places as well.
Yeah. GeoTol YouTube is where I put out some videos on there. Yeah, that and we do on-site training courses and online training courses. That's what we mainly do for companies. But yeah, throw some videos up on YouTube and stuff like that too. Just trying to keep the knowledge going.
Well, that's fantastic. I think it's probably about that time. Thank you all. Congratulations to our winners. And Scott, we cannot thank you enough for the knowledge you shared with us today.
Yeah, thanks for hosting. Appreciate it. Yeah, great talking to everybody here.
Yeah, we've got the best viewers in the world.
We do.
Well, until then, we will see you all in the next stream. We're taking a break on the 4th of July, and we're going to be live again 2 weeks after. So we'll see you all soon.
Cheers, guys. Bye.